Hello and welcome to the podcast According to Sci-Faith, where we discuss topics revolving around the compatibility of science and faith. I'm Joshua Göcking and you're listening to According to Sci-Faith. Episodes 61 to 64, The Final Frontier. Episode 61, Inflation. So, we're back. It took a while, so I think when the last podcast episode was put out, and when I put it out, I said, I plan to restart the podcast after a short break, a short Christmas break in January. So this short Christmas break was a little bit longer than expected, and only now I was able to record new episodes. And therefore, sorry about that, but there's even more to tell you. So now this March or April, it's about 5 years that I started this podcast, at least the German podcast. The English podcast started a little later, but here we all are already also at 3 seasons, so it's more than 3 years that this podcast has been going on. And of course, I'm always thinking about how should I proceed this project. As you see, it's also difficult for me to consistently report new episodes, especially because I have a lot of other things to do, and I also have a full-time job that I work on. So there's a lot of other things I have to do, and therefore I always think about how can I proceed with this podcast, which is the best way to do it, what do I want to talk about in the podcast, which topics do I want to cover. And more I got this feeling that that I want to proceed with this podcast or with podcasting in general in a different way, and therefore I more and more come to the conclusion that I would like to stop doing this kind of podcast, stop doing the According to Sci-Faith kind of podcast. So this will actually, the next 4 episodes will be the last official episodes of the Sci-Faith podcast or the According to Sci-Faith podcast. And afterwards, what will I do afterwards? So I plan on broadening the field of what I talk about in this podcast. So as you know, the podcast is called According to Sci-Faith, and therefore for me it was important to only talk about topics which fall into this category. So topics regarding science and faith, topics regarding these fields. In some cases, I might have deviated from that, but I really tried to deviate not too much from using the staying true to the topic which the podcast is named, because otherwise you would listen to something which you say, a podcast about science and faith, and then something completely different comes. So I don't think that is a good way to do it. But in the recent time, you may have me heard spoken about it on podcasts already. Sometimes I have become more interested in other topics and other areas that also I would like to talk about. And this is especially in literature, in writing, in reading. So I'm a passionate reader, and as you have heard on the podcast several times, I'm also by now a passionate writer. I write not only the book Sci-Faith, the Compatibility of Science and Faith, which is a non-fiction book, but I also wrote some fiction books, from which at least one, so Alien Thoughts, is also available in English. So there's another passion that I go after, and I think this also connects to this whole According to Sci-Faith, but in a different way, because in According to Sci-Faith or Sci-Faith, the vision behind it is to really grasp the truth, so grasp the truth of science and of faith and combine it together. And I think science is always the attempt to grasp truth, to get to the truth of the matter, so to speak. And I think literature or novel writing, fiction, is also a way to do that, a way to try to get to truths that are not necessarily scientific, but truths that are more beyond that, metaphysical truths of faith, truths of life, truths of all this. And therefore to really do what I actually wanted to do, really get in this way of grasping the truths of the world, of life, of everything. I think you have to include that, but this you cannot do if the podcast is called something like Sci-Faith, if this is the topic, because then you restrict yourself to basically only scientific and faith topics, and therefore I sense that it might be time to stop this kind of podcast and really do it in a new way, do it in another way. And this is what I intend to do. And therefore, these will be the last, as I said, it will be the last 4 official episodes on the podcast according to Sci-Faith. Then afterwards I will start a new podcast. In this podcast we will still talk a lot about scientific topics. We will talk about science. We will talk about how we can relate science to faith and how we can interpret science from a faith perspective. But we will also talk about a lot about other things. We will talk about literature, maybe many works, great works of art in literature, and also about other topics. And I also intend to talk more about my books, about the books I'm creating. I got some plans for this to include you in this process. So this is basically the plan, and also it will not only be in audio form, but as you know, there is a Substack that I maintain where also some blog posts about science and faith are already published, and this I will also rename, and also I plan to every episode that I publish, there will be an article on the Substack where you can basically read it, and it will be like that you have an article to read, and in the podcast I will usually say what's in the article, but I will also expand on that in some places where I see fit. So usually it would be the case that if you listen to the podcast, you will get more content, more explanations probably, or more deeper insights. But on the other hand, if you read the article, you get it in short, precise form, without the many airs that seem to come into this podcast sometimes. Sorry about that. But you will get both content. So if you are somebody who say, I don't really get to listening much or listen to podcast much, then you can also read it or share it in a better way, or you can listen to the podcast still, and then you get even in some places deeper insights, more information, and so on. So this is the basic plan how I intend to continue with the podcast. And I hope this is okay for you. I hope you like it this way. I will start just trying it this way anyway, so please bear with me in this. If you have feedback, if you have something where we say maybe you can talk about these topics or that topics, what interests you, just in this kind of area where we are trying to grasp the truths of the world and of life, and also of faith, of course, and talk about these topics. If you say, hey, there's something that I really want you to talk about, then just let me know. Or if you have some kind of feedback then or suggestions, then just let me know. You can use for this the contact form on my website. If you type in sci-faith.de/en and then /contact, you can contact me. You can fill out a contact form and contact me, and then I will surely read what you write to me, and I also try to answer it. So this is how we will continue. And now for the next 4 episodes, I will talk about scientific topics. One thing I want to say still, so if you are not sure yet if this new podcast would be something to you, that's not a problem. Just stay there, stay on the According to Sci-Faith podcast, which will still be maintained. So there will also be new episodes there. This will be episodes from the new podcast that are related to topics of science and faith. So they will, because the new podcast is in a broader way, these episodes will be less. So you will this According to Sci-Faith podcast will not be updated as often. But I think with this you will also get an insight to how this new podcast is and if it might be something for you. So now let's talk about inflation. So inflation is a term that gets thrown around, especially these days, but mostly in a different context than I want to talk about today. So mostly in these days, when you hear inflation, you immediately think of the economy. You think about the fact that, especially currently, the value of the money seems to be decreasing. So you need more money to buy, more money of more value to buy things that you could at earlier times buy for less money. So in other words, everything is getting more expensive. And the reason behind this is inflation. And I don't want to talk about all the economical effects that go into that, although this is also very interesting. But I want to talk about another kind of inflation that is in the term related to what is described by disinflation. So if we just look into economical inflation, then we see, for example, we see that there were cases where this went to the extreme. For example, in the 1920s in Germany, there was something like a hyperinflation, or that's what it's called, where the value of the money was so degraded that at some points, even to buy some bread, you needed 1 billion of the currency in Germany at that time, which was Reichsmark, so billions of Reichsmark just to buy bread. And this value was even more and more degrading, that even you said the people said, if you rob a bank, then it's actually not smart to take the money, but take the stuff which the money is in, so the buckets and so on, because they in the end will be of more value than the money itself. So this shows how this degrading of the value of money, how extreme this was in this hyperinflation in the 20s in Germany. And there are certain other examples in other societies, in other countries, where similar things were happening. And so what inflation basically describes in this economical sense is the degradation of money, of the value of money, due to economical effects. So basically due to the printing of a lot of money, which then degrades the value of the money. So what does this have to do with science? Well, in cosmology, so the science of our universe, basically how our universe came to be, how our universe is built up and so on. In this cosmology, there is also something called inflation, which is cosmological inflation. And there we do not talk about the degradation of the value of money, but since in the economical inflation, you have this case that the value, the money you have or have to pay vastly increases in a fast way in extreme cases of inflation. In this case, in the universe, you have an inflationary period where you assume that the universe was expanding in a inflationary manner, so inflationary fast. So it's a really huge expansion in a really minor time, in a fraction just of seconds, where the universe was inflating in a magnificent way. So just to get a picture of what is meant by this magnificent expansion of the universe. So in the first fractions of a second after the Big Bang, it is assumed that the visible universe went from the size of about a proton to the size of 10 centimeters diameter. And this is really, really a lot, especially if you consider that a proton is so small that not even our best microscopes have been able to resolve them. So it's a really, really huge difference in size and scale that occurred here, and this just in fractions of seconds. So this shows how huge this impact of inflation seems to have been. And what one also assumes there is that at this time, all the powers, all the forces that we know of, so we know of 4 forces. We know of the electromagnetic force, the force of gravity, the weak force, and the strong force. And especially the 3 forces of electromagnetic magnetism, the weak force and the strong force, one assumes that they have been combined to one force, one great unified force at this energy scale. So in this state of the universe, and these theories that assume this are called great unified theories, or for short GUT, and they describe it in this way because what you realize, I'm not sure if we had it on the English podcast, but on the German podcast for sure, but I also think we talked about it on the English podcast, because there is this effect of a running coupling. So as you know, forces are affecting each other by a coupling. So you can, for the coupling for the electromagnetic force, or of course, is the charge. So the particles are charged, and with these charges they exchange, and this is basically the coupling with which they interact with each other. And other forces also have their own kind of coupling, and these couplings have different strengths, different properties. But if you just if you then go into the area of renormalization and so on, which is some mathematical technique in quantum field theory to get rid of terms to diverge into infinity, then you will realize that these terms, these couplings, are dependent on the energy scale where you are, where you observe it from. And this you can understand it, for example, for the electrical charge in this way, that you say, okay, an electron carries the electrical charge, and if I now get to higher energies, this means higher energies also means closer distances. So if I get closer to the electron, then the charge will change, because before the charge of the electron leads to other particles going around, be out of vacuum fluctuations being created and annihilated, and they kind of cover this electron, and therefore the charge decreases. But the closer I get there, the more I get behind those vacuum fluctuating particles that are shielding this electron, and therefore the charge changes. This is how you can physically interpret this effect, but basically it means that the couplings are changing depending on the energy scales that you are on. And then if you go to really, really, really high energies, then it seems that these couplings are getting closer and closer to each other. You need to have the right model to describe it. If you use the standard model, which is the accepted model for describing particle physics, but where we also know that there are some gaps in there still. But if you would use that, then the curves of these extrapolated curves of these couplings at this or this extrapolated graphs of these couplings at these higher and higher energy scales would not really meet each other directly. They would come close to each other, but then they would deviate away. But if you have, in certain theories, in these grand unified theories, you can achieve that at this GUT scale, at this scale, there's the scale where all these couplings are of the same size, so where they all are basically one, and then all these forces are not different forces, but they are one force. So in this way, all the forces are different manifestations at different energy scales of the same source, or of one original force. So this is basically the idea, and the idea is that in this part of the inflationary expansion of the universe, that this has been present, that the forces were united in this one original force. And then you assume that there is a scalar field, like for example, the Higgs field. We talked about the Higgs mechanism on this podcast, which is basically a scalar field is basically a field which to every point in a room assigns one number. So you can have, for example, a temperature field, which is the temperature in your room, and at every place in your room there will be one number which denotes the temperature at this place in the room. This would be a scalar field, and there will of course be different values. In some areas of your room it will be a little bit colder, in others it will be a little bit warmer, but basically it will remain pretty constant, and therefore you have a scalar field where you have at each point one value. There is a different kind of field, which is a vector field, where now let's assume you are in your room and you open up the windows, and it's deep winter, and you just open up the windows, and if it's a large room, then it will start there will be a temperature gradient. So it will start close to the windows, that there will be cooler temperatures, and this will not only be like individual values in this field, but this will spread out. This will have a direction, and therefore what it means to have a vector field is every point in space does not only get a number, does not only get a value, but also gets a direction in which this kind of flow is going. So in this case, if you have the windows open, in which flow does the change of temperature go, and this would be then an example for a vector field. And in particle physics, for each particles you have the same. You have vector particles, you have scalar particles, and the Higgs boson is a scalar particle. As you know, the Higgs boson is responsible for every particle receiving its own mass, and therefore you can see this is basically kind of the value that it gives every point in space. It's just a non-vanishing field value, a vacuum expectation value it's called, that's pointed to every point in space, and with the other particles coupling to this Higgs field, they receive by this their mass. And for the inflaton, which is the scalar particle that is responsible for inflation, is called. With this, you receive you assume a small a flat potential. So this means there is no, like the Higgs boson has this Mexican head potential where it changes depending on where you are located, and this for the inflaton you assume such a flat potential where this does not occur, where it's everywhere the same, and this also means this then yields to a negative pressure, which then leads to this inflationary expansion of the universe. And this is really a huge expansion and a fast expansion. So this expansion goes faster than the speed of light. And now you say, hey, that cannot be possible. Nothing can move faster than the speed of light. But actually it can, because the restriction that nothing can move faster than the speed of light is only for particles and parts of space, and this is due to the fact that causality needs to be restored, and if space itself is expanding in any way or form, this does not affect causality at all, and therefore space itself can expand in a way which is beyond the speed of light, is faster than the speed of light. So there you can see that this inflation assumes a high expansion or a fast expansion of space at a very short period of time. And the reason why we need this, so the reason why this is assumed to be the case is there are many reasons for that, and one reason is that the universe is assumed to be homogeneous and isotropic. So this means that the universe has the same shapes and forms, and in all directions it looks basically the same. So for this to work, the universe or all these stars and galaxies have to have interacted with each other, and this cannot occur when the expansion of the universe is as slow as it was assumed before. But if it is the case that there is some inflationary period where this happened, then this can actually be the case. Also, there's the flatness problem. So as we know from general relativity, gravity is an effect of the curvature of space. So space itself is curved, which you can basically assume like you have a sheet and you expand it and hold it tight, and then you put things on this sheet, and then the even if you hold it tight, it will decrease, or there will be holes in it, and in around this the planets or things can move around like planets. So this is basically what's happening. So it's gravitational objects or heavy objects like the sun, like the earth and so on, they curve space, and therefore objects that move around these objects are put on a trajectory around them, and this is basically the effect of gravity. So in this sense, gravity is not actually a force, but it's something like a pseudo force, something like the Coriolis force, if you are familiar with that. So something like a force that isn't actually a force, but is an effect of something else. And this is the way gravity is described in general relativity. And this means that space needs to be curved for this to work, but one realizes that this curvature of space is really, really small. So it is there, of course, we have gravity, otherwise we would not have gravity if space would not have some curvature, but it is really, really small compared to what it could be, and therefore there is an exact and there needs to be an exact tuning of the density of matter and the kinetic energy. And this is not possible this would be needed for a normal expansion. It would be really needed to be fine-tuned, and if you have an inflationary expansion, this is not needed. So there it is even expected that something like this happens, and therefore this can also solve this problem. And there's also some issues like the density fluctuations in that lead for things like galaxies, or like bunches of galaxies, many galaxies at one place. This can only be explained this can easily be explained by fluctuations in the inflaton field. And also there are theories which include magnetic monopoles. However, these magnetic monopoles could not yet have been found, and this could be explained with inflation, because inflation would explain why they are so hard to find. So basically, all these problems are fine-tuning problems. So basically what it says is our universe, as we perceive it, as we see it, is or has too much order for it to have come into place like we have assumed before. And this is really interesting because it shows that there's too much order in the universe as the physical theories that we had up to now would expect. And this can, of course, also be interpreted as a sign, therefore, as a sign that the world indeed was created by a creator who put this order into the universe. And this, in the same way, also doesn't need to mean that there is no effect of inflation, or there has not been an effect of inflation, but it can be true at the same time, because if you have read my book Sci-Faith, the Compatibility of Science and Faith, then you know about this. There is this example that I bring. If you have, for example, someone playing Tetris, the game Tetris, and you just watch somebody play this, but you don't know that there's a player behind it. So you just see these shapes flowing around, moving up and down, turning and so on. And then you see, okay, what's the goal of these shapes is to build a complete row and then to annihilate this row. And you see the end of the world is when this is not possible and they are all stacked up to the limit, and then this world is ended. This would be the apocalypse in this game. And then you start, because you don't know that there's a player behind it, you start to say, okay, there are certain shapes that seem to attract each other. There are certain shapes that seem to be attracted to certain areas, because the player wants to win, and therefore he will consistently act similarly to achieve the same result. But you don't know that there's a player behind it, so you assume that this is some natural laws that are behind this, and then you put all these natural laws in that describe all this, and then you get basically some physics of this Tetris game with which you can describe the whole behavior of the game. But still, in all this, there will be a player behind it who plays like that because he wants to play good, but not because he's bound to act like this. So he could at any place break all the natural laws of his behavior that you have set up, because he's a free human being, but still you would describe his behavior in these terms. And this, I think, is the same with the universe, with the world, that many things that we describe in nature are actually the working of God behind the scenes, basically, and us describing it is basically describing what God does in the background. So this is a way in which you can bring both things together without saying, physics does not understand this. This means God is actually behind it. Because if you would argue like this, then you would need to say every time when physics can explain something, you would need to say, okay, then God isn't behind it. That's nonsense. God is behind everything. So therefore, you with this example, you can understand how this can work together, and how things that are really well understood scientifically can still, or are still, with God's working behind them, and also how things we cannot understand, where we still can know, okay, even if we find a scientific theory that can perfectly describe these effects, this still does not mean that there isn't a God behind it. And I think even this effect of the seeming effect of inflation, that it yields the universe to be in more order than it is expected to be, shows that there is the working of God behind it, who created a perfect universe, perfect for us humans to live at, and fine-tuned it for life on this planet, perfectly for us to live there. And at the same time, this can also be described by some mechanisms of inflation. So, having seen this, we need to also accept that inflation right now is not a verified theory. So there is no evidence for it, no direct evidence for it that you could say this theory is indeed confirmed. However, many scientists assume it just to be true, because many things can be only described, or up to now there's only the description of inflation, or it's the most prevalent description that we have of many of the effects that I also mentioned. So many are convinced that inflation is something that occurred in the beginning of the universe. However, there are up to now no direct evidences that this is indeed the case, and up to now this theory still is considered to be not confirmed. However, also some physicists criticize this theory exactly for that. They say this theory is impossible to disprove, impossible to falsify, and therefore it just has to be true because it cannot be falsified, basically. But this also is not of huge value in scientific theories, and has then the same value as some of the bad creationist theories or other bad pseudoscientific theories. So with this, I do not mean that all creationistic theories are necessarily bad. Therefore, I do not have enough knowledge of them, but there are some of them who are not really well thought out, and there are also other pseudoscientific theories who are not well thought out, and this would put them on the same level, because a theory that cannot be falsified can also not be verified, and therefore is not of any value at all. So there are also some alternative theories to describe this. One interesting alternative theory is the one of a variable speed of light, where you assume that the speed of light has not been constant throughout the era of the time of the universe, so that the speed of light, for example, could have been a lot faster in earlier times and slowed down up to now over these eons, over these huge time scales. What this also would mean, of course, is that time itself would not be always in the same speed, at the same speed. Then time would have moved differently in the past. Of course, the people there would not have recognized it as such. Time would pass for them like for us, because everything around them would pass like them, would pass in the same sense. But if one would compare it with us today, then one would see that time then was moving slower than it is moving today, or faster, depending on which what kind of variation in the light speed you would assume. And this is also interesting, because it could maybe explain why the time scales, for example, if you go after the Bible, if you look after the Bible, what the Bible uses as time scales, and if you look what the Big Bang Theory and the theories of the universe and of nature use as time scales, and these differences might be even resolved by such a theory. That's just speculation. It doesn't need necessarily to be this way, and it also doesn't, of course, mean that if the speed of light is proven to be a constant throughout all ages, the same throughout all ages, then this doesn't necessarily mean that this doesn't mean that faith and science cannot be combined because of this issue. No, there are plenty ways to interpret this and to unite this into one. But this is how inflation basically works. I hope you could understand the basic concepts of it. But I think the really interesting part of it is that it shows that our universe has more order than we would have expected without this inflationary theory. And this shows to me that really God created this universe who ordered everything perfectly for us to live on this in this world. Episode 62, Cherenkov radiation, superluminal particles. So in this episode, I want to talk about Cherenkov radiation, which is a really interesting phenomenon in physics, especially also relevant in particle physics. And this is radiation that results when particles move faster than the speed of light in the medium. So now you say, how can this happen? The speed of light is the final frontier, basically, and nothing can move faster than the speed of light. That's true. However, that is what's meant by this, and what's often omitted is the speed of light in a vacuum. So particles can only or can at most fly as fast as the speed of light in the vacuum. However, if you are in a medium like some matter, water, air or something else, then the speed of light is reduced in these mediums, and therefore you can, for example, also observe different effects, because the speed of light is not the same in every medium, and in different mediums it usually is at different speeds, and this leads to many optical effects that you might even know from your everyday light. For example, if you see light passing through water, from the air through water, you will see that there is an angle at which this light gets in, so it will not go straight through, but there is an angle at which it will enter into this other medium, and the reason for that is exactly the different speeds of light in these different media. And what the reason of or how this works is basically that if that light always tries to go, or always does go the way of the shortest time, so the fastest way, basically the way that is for the light where it is the fastest, basically, where it has the shortest times of arriving. And this you can imagine somebody is drowning in the sea, and there's is a lifesaver. He tries to save him, and he sees him drowning in the sea, and then but he's on land, of course. And then what he does is he first will probably go most of the area by on land, and only when he's closest, the distance between him and in the water is the closest, then he will swim and try to save him, because he's faster on land than he's in the water. But if you just look at the trajectory that he will go, then you will see that he did not go on a straight line, which would be the closest in distance, but he went in one way, and then he made a turn and went in the other direction. So he changed directions, because this way it would take less time for him to achieve the one he wants to save. And this is the same how light behaves, because light also travels through the medium, and when it travels through a medium where it is faster, then it will go faster through that, go first through that, or go most of the area through that, and then it will only enter into the other medium. And by this you get these breaking angles of light entering into different media, and there are many optical effects that come this way. Also, mirages are the reason how they can come is in the same way as this works in the same way, or the reason behind it is are these physical effects. So now we can understand that light is smaller in some medium. Light in the medium is smaller, is slower than light in the vacuum. However, particles, so not necessarily light, but other particles can in many cases move faster than this speed that the light moves in this medium, because they aren't necessarily slowed down as much in this medium. So if you have this case that a particle can, for example, you use water, and a particle, let's say, can move faster through water than light can move through this medium, then you have this effect that the atoms are being polarized. So this would happen anyway. So there's a charged particle, or let's say there's a charged particle going through this through this medium, and then of course the charges of the atoms. So an atom consists of protons and electrons, and they are polarized then, because if it's for example an electron going through water, then the electrons in the atom, they will move away from where the electron is moving, and then the positive charges or the absence of the negative charges will basically lead to a positive charge in that direction and a negative charge in the other direction, and this way the atoms are polarized. And this is a temporarily changing polarization that gives a dipole moment. And as we know, a temporarily changing dipole emits radiation. So this is emits radiation, and therefore light would be radiated from these atoms. However, this light, if the electron travels through this medium below the speed of light in this medium, then this light is interfering, and it is interfering destructively. What this means is that everywhere where there's a wave trough, there will also be a wave peak that basically annihilates this. So they do then annihilate each other, and this is a destructive interference, and so none of the light will remain after this has occurred, and therefore there will be no radiation in this case. However, when the particle moves faster than the speed of light in this medium, then of course the light is slowed down is slower compared to the electron, and therefore it's moving faster than the speed of light in there, and therefore this polarization will also occur, but the interference will then not be destructive, because the particle will be already polarizing atoms in front of the light that is already radiating, and therefore the interference will then become constructively, and this will then lead to actual radiation that will be emitted, that is real radiation that you can also see. So there's one example where you can really see this is in a nuclear reactor. There you can see Cherenkov Strahlung being radiated. It's mostly in these cases it's mostly blue, and it has kind of a cool look. So this is how this works. You can understand it. It's in a way similar to if you have it with sound. If you break the sound barrier, this is similar things are happening there, just in the area of sound. So this is how this works. And one interesting thing is also there are things called Cherenkov lightnings. So this effect not only occurs in nuclear reactors, it also occurs in cosmic radiation. So in space, basically, there's cosmic radiation, and when this cosmic radiation passes through a medium, then this same effect can occur, because then it's faster than light in this medium can travel, and then this can lead to lightnings being radiated there. And this can also happen with astronauts when they are in space and they have their eyes closed, that these particles flow through and can then basically make these lightnings in the midst of their eyes. So they basically see this Cherenkov light although they have their eyes closed, which is a pretty fascinating effect. Also, this Cherenkov's radiation can be seen when neutrinos. Neutrinos are particles. We talked about them when we had a podcast about neutrino oscillations and different other things. They are really not interacting much with nature. They only interact with the weak force, but with this weak force, they can punch out basically electrons from atoms, so they can throw them out if they interact with them in the weak force, and this will lead to Cherenkov radiation. And this is one way in which you can measure neutrinos directly. There are different ways, but mostly it's really difficult to measure them because they interact so weakly. Basically. So for example, at LHC or at many particle accelerators, you only measure neutrinos by realizing that there is some energy missing. So that's missing transverse energy. That's basically how you resolve neutrinos in particle colliders. But another way to do this is to have big water tanks in which then the neutrinos punch out electrons out of the atoms, and they then radiate Cherenkov radiation because they have speeds that are faster than light in this medium, and this leads to Cherenkov radiation. And then when you see this Cherenkov radiation, then you know, there were some neutrinos that punched out some electrons, and then you can do measurements on the neutrinos, or you can measure more of the properties of the neutrinos. And this is also done in the Mediterranean Sea. and there is an experiment where they try exactly that, and what they measured there is pretty fascinating. They measured a neutrino with the energy of 220 peta electron volts. This is really, really a lot. So just to compare it, an electron itself has 511 kilo electron volt. This is many orders of magnitudes below that. So you would just see a 1,000 kilo electron volt are one mega electron volt, and 1,000 mega electron volt are 1 giga electron volt, and 1,000 giga electron volt are 1 tera electron volt, and then 1,000 tera electron volt are 1 peta electron volt. So there are many order of magnitudes above it, and even the heaviest particles that we know of, that's the top quark, that has 172 giga electron volt, which is still 1,000th of this energy, but even this top quark is already of the mass of about a gold atom. So you can see how heavy this particle that they have, or not heavy, how energetic this particle, this neutrino that they have measured there is. So it's not really clear where this comes from. One assumption is that it could be of some processes or could have been from some processes in black holes. However, if this were the case, then we would already have measured this at different places. So it's not really understood why this is, how this can be, how we can measure a neutrino in such high energetic, with such a high energetic value. It's not really clear why that is, and this was in recent months or weeks was one huge finding that was pretty interesting. Yeah, so I think we can interpret this in the spiritual. So I'm talking about Cherenkov radiation in general. We can interpret this in the spiritual, that in this world, in this medium of this world, God can move faster than even this world. So the light in this world can react. And this leads to light being emitted. So this leads him to be the light of the world, or also us who are one with God, who are born again in Christ Jesus. We can then be this light of the world, which is basically by us moving faster through this medium. We can react faster if we trust in God, if we trust in His guiding and so on. And then we can be a light in this world like this Cherenkov radiation. And also, this light can then be seen, as you had it with the astronauts, can seen even if asleep. So even if the world is sleeping, if nobody sees it, this light can even be seen because it passes right through, basically. And so this is, I think, an interesting spiritual interpretation of this physical effect. Episode 63, Einstein's Blunder. So in this episode we want to talk a little bit about general relativity and some conclusions that you can derive from this theory. So as you know, general relativity is a theory that was brought up by Albert Einstein. It was his big achievement, which basically extended his special theory of relativity, which he had first, where he basically introduced this concept of the relativity of space and time, and it extended this to include also gravity, which was in the special case not included yet, but it of course had to be included. And in general relativity, he considers that space time or space time, so space and time is also a dimension of space in the sense. So space time, that this is curved, so there's a curvature of space time, and this yields leads to the gravitational force. So you can imagine this like a sheet that is spread out, and on this sheet then you put these basically these heavy objects, and if they they curve then the sheet, and then the particles or the things you move around on the sheet, like marbles or something like that, they can move around these heavy objects like planets around stars. So this is the basic concept, that space is curved in this way, and that therefore this leads to when they are heavy object, they curve space or space-time, and then objects move around them because of this curvature of space. But actually they would be in free fall, but this curvature leads to them acting like they are under a gravitational force, and this, in this sense, gravitation or gravity is kind of like a pseudo force, because it's actually particles or objects in free fall that are affected by this curvature of space. So if you build up this theory, so the main part of this theory are Einstein's field equations, and if you have these equations and then you try to solve them, which is not easy at all, but there are certain people who came up with solutions to these equations. One interesting person is Schwarzschild, who wrote the conclusion or wrote the solution to these equations, not by simply studying in rest at home. No, he was in war. He was in a lazaret and or in a hospital, war hospital basically, and there he was solving these equations. And this was one of the first solution to the Einstein's field equation, the so-called Schwarzschild solution. There have been other solutions that assume different things. So basically, you cannot solve these equations completely analytically. You need to assume something about space or about the thing you consider, and then you can find a solution or get to a solution this way. And what is interesting, what in these solutions came up, or what already in the Einstein's field equations comes up, is that that if you solve the equations, then basically you have most of the time an expanding universe, and only one way in one way you can get around it, and this is by introducing in the Einstein's field equation a so-called cosmological constant. And that's exactly what Einstein did, because Albert Einstein did not believe that the universe is an expanding universe. He did believe it is a static universe that does not expand, and therefore he was not comfortable with an expanding universe in his equation, and therefore he introduced this cosmological constant, and he prepared it such that the universe remained static. However, about the same time, or in the 20s and 30s of the past century, there were experiments that showed that this seems to not be the case. Especially there was Edwin Hubble. You may know this name from the famous telescope that is named after him. And he was an astronomer, and what he did is he measured the Doppler shift of the galaxies in our universe. So the Doppler shift you might be familiar with. So if you know the sirens, or for example police or the fire department and so on, if you know their sirens and you listen to them when they come towards you, and then or you listen to them when they drive away from you, then you might have noticed that it kind of sounds different depending on whether they drive towards you or away from you. And the reason for that is that these sirens, they go with a frequency. This is sound. This is a sound frequency, and there it is so these are sound waves. And here it is like that if a sound wave is in an object that is moving, then the speed of the object that is moving is basically added to the sound wave, of course, just like the speed of the car that you are driving in is added towards you. That's why if you would brake abruptly, your body would still go forward, and you need to have a seatbelt to stop that from putting putting you in danger. And in the same way, it is with a wave that the speed is added to this wave, and this leads, since the wave has a fixed speed at which it's spreading out. In the case of the sirens, it's the speed of sound, and since then, therefore, this speed cannot be added to the actual speed of the wave, and therefore it is added. It is transformed into added to the frequency of the wave. So the frequency, if the object comes towards you, so if the police car is driving towards you, then the sound wave will have a shorter frequency, and if it drives away from you, it will have a lengthened frequency, and therefore it will sound differently to you. So this is the Doppler effect, and this is also this effect of the Doppler shift. And the same thing happens with light. And so Edwin Hubble was measuring this, and he realized, so with light it will be the case, if something moves away from you, then it will be shifted also to frequencies more to the red spectrum of light, and if it comes towards you, it will be shifted to frequencies of the blue spectrum of light, so the higher frequencies. And this is what Edwin Hubble measured, and he saw that most of the galaxies that he measured were shifted to the red spectrum, so they were moving away from us. And this can only make sense, or there are also different explanations for this, but this mostly makes sense if you assume that the universe is expanding. What's interesting about this is that already years before there was a Belgian clergyman called Georges Lemaitre who also assumed this and concluded that if this is true, then the universe was once all compressed into one point from which it spread out. So there was a clear beginning of this universe, and it was not a static universe which has been there forever, but it was a clear beginning of this universe. And this was really controversial, because up to then everyone thought that there was a steady state universe, that this universe was basically around since forever, and one was also arguing that using this to argue against the Bible, because one would say, the universe was around forever, your Bible tells us that there was a beginning, which is nonsense. And Lemaitre came to this conclusion from the scientific side that this is not to be the case, that there actually was a beginning, and that this was the so-called Big Bang, or as it has been later called. And Lemaitre needed to argue a lot with Einstein and convince him of this theory being solely based on scientific fact and not on spiritual beliefs, because Einstein and many others, I think, rejected this theory in the beginning because it was really, really close to the Christian faith, to the faith in a creator. And therefore, Lemaitre had endeavored in a major way to really convince him, no, this is just my scientific work, just looking at the science, looking at the scientific facts, and they lead in this way. And in the end, Einstein came to agree with that, came to agree with these findings, and considered this cosmological constant later to be his greatest blunder. And this is the state that it had been, that this cosmological constant, which is denoted with the Greek letter lambda, that this has been set to zero up until about the 90s. But then there were different measurements made that even showed something more. They showed that the universe is not only expanding, but it showed that the expansion of the universe is increasing, so it's accelerating. So we have not only a universe that is expanding, but a universe that is accelerating in its expansion. And for these measurements, these were done by observing supernova, so star explosions basically, and they were awarded with the Nobel Prize several years ago. And this was a huge discovery, which needed, of course, adjustments in the theory to be able to describe this. Because the expansion of the universe, if you look into Einstein's equations, you see that this is made possible by matter, by basically the presence of matter fosters this expansion of the universe. But with the universe expanding, the density of matter, of course, decreases, and therefore also the expansion of the universe decreases. However, if you assume that there's an energy in the vacuum, which is physically not forbidden, then if the universe expands, then this will also be expand in the same way, and this will lead to an accelerated expansion of the universe. And this you can achieve by using a cosmological constant and setting them to non-zero, but to a certain value, which allows for this accelerated expansion of the universe. And this energy is called vacuum energy, or also dark energy. And today we know that this is about 68% of the universe that consists of this dark energy. And if one also consider that we assume that about 25% of the universe consists of dark matter, then you see which is also not understood. So these 68% dark energy, we know they might exist or they have to exist to allow for this accelerated expansion of the universe, but more we do not know about this energy, especially also not the specific value. And the other 25% of dark matter, we still also have no explanation for what that really is. So there you can see that about 95% of this universe is not understood by us, and only the 5% which is the baryonic matter is mostly understood by us, but there are also many gaps that we still not understand. For example, baryogenesis, how the CP violation and so on. There are many things that we do not understand about this part of matter either. But still, this shows how few we really understand about this universe, and it's interesting that we are kind of in a time where we actually know, or seem to know, how few about this universe we actually know or actually understand. But in today's standard model of cosmology, this dark matter and dark energy is combined in this model of called lambda CDM. So lambda for the cosmological constant, and CDM is the abbreviation for cold dark matter, because what we know about dark matter is that it's most likely to be cold dark matter. What is meant by that is that this dark matter is not relativistic, so the dark matter particles do not move at the speed of light or close to the speed of light, but they are significantly below the speed of light, so they are slow, they are cold in this sense, because if you look at what makes temperature, what makes hot temperatures, it's particles moving fastly. So if you in the physical sense talk about something being hot, then you talk about something being some particles and they're moving really fast, and in the cosmological sense even in relativistic speeds. And if something is cold, you mean it is moving not fast and it's moving in not relativistic speed, so far below the speed of light. So this is the cosmological the standard model basically, and there's assumed that there is some kind of dark energy and some kind of cold of dark matter which is most likely cold, and there are certain models to describe these. And now there was a new finding from a science collaboration called DESI. The DE in DESI is for dark energy, so they are measuring dark energy. And what they measured is that the acceleration of the universe is decreasing. So we had measured that the acceleration of the universe is present, and now they measured that it seems to be decreasing. So first of all, one needs to say this is not a safe measurement yet. They have this to a certainty to up to 4 sigma, which is a lot already. So just to understand what this means, you might be familiar with this kind of IQ meme where there are two sides on the left and the right, so on the low IQ side and the high IQ side, who basically say the same thing, and only the one with an average IQ thinks he's smart and say something different which sounds smart but is actually not smart. So you might be aware of this meme, and the curve that you see there, this is basically a Gauss distribution, a Gaussian. And this curve appears in statistics again and again. Basically, everything that is distributed in a statistical manner at some point will converge into such a Gaussian. So usually it starts with a binomial distribution, then it goes over into a Poisson distribution, and in the end, for many statistics, it goes over in such a Gaussian distribution where in the middle you have the mean, the mean value, and then on the outer sides you have the extreme values and the quantiles and so on. And so what you will have there is you will have also the width of this curve, and the width of this curve is related to the so-called standard deviation. This is just a statistical quantity that you can compute, and this basically describes the width of this curve. And for the Gaussian, it is the case that for also the bell curves, there is the case that in the distance of one width of this one standard deviation, there is 68% of all these points. If something's is distributed statistically like such a Gaussian, like such a bell curve, then 68% of the measurements or of the statistics will be in this between the mean and the first standard deviation. So this width in the middle. So, and if you then, this would be, and the standard deviation is often denoted by the Greek letter sigma, and this would then be a 1 sigma certainty. Then you go further to 2 sigma there, it is 95% of the values that are in there, and at 3 sigma it's already 99%. So what this basically means is that the probability to find a measurement that is outside of something like 3 sigma, that the probability that something like this occurs is lower than 1%. And if you have 4 sigma, then it's even far lower than 1%. And what is needed for being a scientific discovery is actually a certainty of 5 sigma. And if you have achieved this, then you know for high certainty, a high percentile certainty that all the values that you measure will be in, or most of the values in this area will be in this area, and then you are pretty certain that the value that you assumed for this the thing you want to measure is the correct one. And as I said, in this measurement, they are certain to a degree of 4 sigma that this the acceleration of the universe is decreasing, which spoken in scientific terms means that it is not a discovery yet, but it is something where people lift their eyebrows, so to speak, because everything that starts at 3 sigma and goes up to 5 sigma. Everything in this area is usually where scientists start to get interested. Doesn't mean that it always will be the step before the discovery coming. There were also many cases where some findings of about 3 sigma and more were reported, and people were getting excited and throwing out papers and so on. But in the end, it was shown that this was just statistics and background statistics, so it vanished again after further measurements. So this can also happen and also occur. So there you are never certain that you really have made a discovery or that this will lead to a discovery. So therefore take this finding with a grain of salt. But what this would mean, if this is correct, what it would mean is that the cosmological constant is not a way to describe what's actually happening, because the cosmological constant, of course, is a constant. It's constant, and here it would need to change because the acceleration of the universe is decreasing. So something is really changing. changing. And what you then, if you assume that the cosmological constants therefore gets smaller and tends towards zero, then it's interesting what would then happen, because at some point it would go below zero, and then there could be the effect would be that probably that the universe would not only decrease in accelerating, but it would accelerate in a different way, and so it would be crushing back together. And this is one also of the theory how the universe in someday might end, is that I think it's called a big crunch, that basically as the universe was expanding and expanding and expanding, at some point it will crush back into one point. And there are also theories that think of this as a cycle, basically that there's a big bang, then the universe expands, and then it basically crashes back into one point, and then there's another big bang, and so there is some eternal cycle of universes. Basically, this is also in some theories, but this of course is all theoretical. There is no evidence at all for any of that. That's just a speculation, and I'm not sure if you can really confirm this in a scientific manner anyway, because it's just speculative and there's no way to measure things that are beyond our scope. But this is the thinking. This is that shows the open questions there, and so there are many interesting things happening there. And I want to also interpret this in a spiritual way, this accelerated expansion of the universe. I think it shows that God is always on the move, that he's always moving, and that he even increases in what he's doing, that he even accelerates, that he's even accelerating in his moving forward. And this is also for us to know that God is always progressing, he's always going forward, he's going forward with us, he always has more for us than we could imagine, more above and beyond what we could dream or think of. And this is who he is, this is what he does, and it is even shown in his creation, in the world he created. It is shown that this is what he does, this is how who he is, and therefore we can believe that he has only the best things for us. Episode 64, Created for a Purpose. So many times on this podcast, I think I talked about it already, that I'm also writing some articles, and I wrote articles for this magazine Studium Integrale of this Studien of the study group Wort und Wissen in German, so word and knowledge in English. And there in this magazine, I recently found an article about some article other scientists wrote, which was called Evolution on Purpose. And this is was a discussion among evolutionary biologists, where they were discussing something like evolution on purpose, so that they saw that there seems to be a purpose in nature and also in evolution, that there are things that are purposefully created, so to speak, and that even with all the concepts of the theory of evolution, you cannot omit that fact. You cannot remove the fact that there are many things in the beings that have evolved, that there's still some purpose that you can see in there, that you cannot get out of it. And they were trying to find a way to kind of scientifically, in the manner of the theory of evolution, to describe that. And this kind of seems to be nonsensical, because the theory of evolution, if you look at it, was kind of created to make this purposefulness of animals and of humans obsolete. Because and in this way the theory basically eats itself, and it doesn't work anymore, because this is basically what it tried to do. So first we need to talk about what this really means. So the theory of evolution is not therefore disproved in some way, because you need to distinguish here between what you mean by theory of evolution. There are certain kinds in which you can understand this. So there's one thing which I think you have to accept is really factual in nature, and this is what many call microevolution. So this basically means adaptations that organisms do to their surroundings, which yet doesn't mean that they go over into other species. So this does not assume that there's like a tree from which where you see beings having descended from. So basically that apes and humans share the same ancestor and so on, where you do not go as far as to assume this would be macroevolution, but where you just acknowledge that as it can be shown in many cases, that there are species who adapted in a certain way to their natural environment, to their surroundings, and so on. But if this, I think, is established by science that this is really the case. However, macroevolution is in many ways it does not have this clarity, and it has many problems where things do not add up. So for once, there is this effect of convergence, as it is called. This is basically that if you look at many species and try to get to the same ancestors, try to get basically a pedigree, a genealogy of species in there, and then you will still find some species who have the same kind of attributes or features, but they have different genealogies. So they come from different they are not related in a evolutional sense. If you assume macroevolution, they are not related in any way. So the types or the things that they have developed must have become individually. So they need to individually have developed these traits, although they are pretty similar in the end. For example, there are species who have tusks, like elephants, for example, or also ancient species. And many of them have pretty similar tusks, but they are not related in any way. Or in macroevolution, you can find a way to have them relate to one another, and this kind of kills the whole point of it, because it basically says that they have these things individually or evolved individually. So why, since you assume macroevolution, because you see, hey, there are similar traits that these species have, so maybe they have a same ancestor, and then you compute all this through, and then you see there are still species who have similar traits, but have they evolved separately without any relation to each other. Then you can basically drop the whole thing, in my opinion, because you don't have something more of explanation power, because you still need this effect of things coming into being separately from each other. And there are also many other things. For example, complexity is also one issue. That, for example, you for many features you have species or animals or humans have been developed together, and this would not make sense. For example, you could not have the large brains as humans have them without the womb of the females of the species also to have been expanded in a way that these big brains basically can go through the birth canal. This would only be possible if both things would have evolved at the same time, or one thing first evolved and the other evolved behind it. But then it wouldn't make sense, because then there would be purpose involved in it. Then there would be a clear structure, and also evolution also always assumes that everything that there is basically a random mutation, which then is better adapted than other mutations or the state as is, and therefore they then win out, basically. This is how you get rid of all this purposefulness and so on. But this would then not work, because if you have just one part of the whole thing developed, then you don't have an advantage. You have a disadvantage, because you have the feature that you actually want to have, you don't have it, and you have just the mechanism to have the feature in a later way, and then you are actually at a disadvantage, but later you would be at an advantage, but you don't have enough time to wait for this mutation which makes you advantage, because now you're at a disadvantage, and so it in an evolutionary way it would die out before the feature can really come to pass. So therefore there needs to be some purposefulness included in nature, and this cannot be in no way ruled out by the theory of evolution. And these scientists, they came to this conclusion that this actually has to be, and that there has to be some kind of purpose in the way the mechanisms and the animals and so on evolve. And therefore you see there, this you can also only explain with one thing, that there is some design in how the beings are created. And still they try to theorize around this fact that this somehow might work without a creator, or without destination, without destiny, without a purpose and so on, but that there still might be some purposeful element in there or somewhere or something like that. And this reminded me of the scripture in Romans 1 verse 22, which basically says, although they claimed to be wise, they became fools. And this is basically what you see often in this way, that you can... I mean, this relates also to the meme that we had about before, about the Gaussian, about the bell curves. I think it was in the episode previously, but there you can also see that you can come to this arrogance, to this thinking of you're that highly, that smartly, that you think you are wise, but actually you have become a fool. And this is here the case, because it's obviously the case that what these signs show, what it shows, that there is a purpose in how the species have evolved, or what the species have developed in their beings, that there is a purposefulness, clearly shows that there must be more than just random mutations that win out in some survival of the fittest principle. There has to be more to that, because it cannot describe it this way. So there has to be design, there has to be something beyond that. And I think scientists often run into this danger that in arrogance and in pride, they think they are smarter than they are, or they think they are wise, and then have become fools, because they cannot just take the fact, which this clearly shows, that there has to be some purpose involved in this, and that this purpose means there has to be some design, and this design has to come from somewhere. This cannot just occur naturally. There is not a natural principle of design in this world, but there has to be design. Always shows that there has to be some conscious mind behind it somewhere, and this is what we would basically call a god. So this does not necessarily mean that you immediately need to believe and say, okay, there seems to be some design in this universe, so therefore there is a God. No, this is not what you have to do, but you need to acknowledge the design. If you see it clearly, then you need to acknowledge it and accept the consequences that come from it. That there seems to be something that designed this world, there's something that designed this universe, that there seems to be some purpose that is written into this universe, that we are not simply some products of random interactions, but that there is really some purpose that is written into our nature. And I think this is really important to understand this, because otherwise you cannot do science this way, because then you clinch to theories that are not that fruitful anymore, and you miss the theories that might be a lot more fruitful than those. And I think this mentality you do not only see in science. This is kind of the mentality to you can see it also in art, and this is kind of this mentality, the delete Jesus mentality, you can call it. So it's basically what you want to do in science. You want to, the theory of evolution, it's a pretty successful theory, because it could describe many things, especially in the area of microevolution. But I think the problem it had from the beginning is that it was intended as an explanation how a world can work without a God. It was specifically intended to remove God out of the equations of science, and this is worked fine for some for some time. For a time it worked, and in some areas it works fine, but at some degree you cannot go on like this, because if there is a God, then somewhere he needs to show up. And I don't say that you need to write into an equation, okay, this is what God is. That's not what I mean. But if you rule out God completely from the equations, if you rule out the possibility of a God completely from the equation, then this is just as bad as writing him into every equation, because it will be just as bad, because then you also have made a decision about what you think is the reality beyond what science can state as the reality, as you have before. So therefore, what I'm in favor of is to be agnostically, truly agnostically in a scientifically way about what if there's a God or if there's not a God, and basically let the science lead you as where it leads you. And if this is something where it's pretty apparent that there has to be some designer involved, that there has to be some God involved, then you don't need to state it explicitly, but you have to state the equations and the findings explicitly and clearly, that this is without any fear that this might lead to some creation, and a God of creation, a creator, might be more probable than not. You just need to let it lead in this way. And I think in art you can also see often this mentality where basically this delete Jesus mentality, where you want to write God out of the equations, although he's clearly in them. So one example for that would be Dostoevsky, Crime and Punishment, which is a book which maybe in a later podcast or the new podcast I will talk about it some more. It's a pretty fascinating book. I recommend you to read it. It's really great. Therefore, I will not try not to spoil you much of it. But in the end, there is some scene where basically he has committed to his crimes. This main character, Cherenkov, he has committed to his crimes, and then basically he has this moment where he says, hey, this woman that I knew, she had this New Testament and she believed in God and so on. And now that I have come clean, basically, this God could also be something for me. He could be the right for me, right? He has this New Testament that he starts reading, and so it's pretty obvious that he basically became a Christian in the end. And this is oftentimes still completely ignored or ruled out, or Cherenkov is stated like some social liberator or something like that, depending on which political ideology one has or one hasn't. But still, this is actually not what's written there. It's clearly, every work of art you can interpret in different ways. That's fine, but it's clearly written there about him coming to Jesus, coming to Christ, finding Christ. And if you ignore that, then you ignore parts of this work of art, of course. Another case which maybe makes it more clear is the movie Walk the Line. It's a movie about Johnny Cash. And Johnny Cash, it's a biopic about his life, of how he started, how he became famous, and how this worked out for him. And then basically what happens is that he goes into drugs, and he has a lot of affairs, his marriage falls apart, and so on. And he's really a mess. And but in the end, he kind of turns around. He goes to prisons and sings for them, and has really his life turned around and sobered up, and so on and so on. And this, in the movie, it kind of just happens, and he kind of has some kind of wake up call and thinks, okay, maybe I shouldn't do all this drug related stuff and so on, and he does other things. But in reality, what happened was that he became a Christian. He came to Christ. So I think he grew up in a religious way. So he also knew some of that. And then when he became famous, he lost his faith and went into drugs and all this stuff. And then in the end, he got back to his faith. He became a Christian, and therefore his life turned, his life changed, and this was observable for everyone. This was to see for everyone, and this was the change that occurred here. But you cannot really understand this change, or how this change came about, without understanding that he really came to Christ, that he really came to Jesus, that this was part of his transformation. This is not to say that there are no people who, without having such a moment, change their life in one way, and you can argue about what this really means, or how much of faith is involved in there. This can be open up for debate, okay, but in his case, in the case of Johnny Cash, this transformation came by his faith, came by the fact that he became a Christian, and therefore you have to show this accordingly, otherwise you are leaving it out, otherwise you're basically lying. And in another case where you could see it in a similar way, which is one example which I also want to mention, is Unbroken. It's a movie about Luigi Zamperoni. He was basically a Olympia runner, and then he was in the Second World War, and he was encamped by the Japanese, and he was brutally tortured there, especially by one warden. And after he returned to the US, he was part of Billy Graham's revival ministry, and he really had this revelation of forgiveness, and he reached out to this one in Japan and said, hey, I want to meet you, I want to forgive you, and so on. He never reacted, but he was preaching this great message of forgiveness, this powerful message of forgiveness, with all he had to endure, and he managed to forgive the people who were torturing so badly. And so it's a great testimony of power forgiveness. However, the fact that this came about he turning his life to Jesus, to coming to the Lord, is never mentioned. It's in a movie, it's never mentioned. It's completely ignored, and this is of course not honest. This is what led to his transformation, and therefore it needs to be in there if you really want to have basically the truth. And this is not to be here critical about some things. You did not mention that my heroes are all Christians or something like that. That's not what this is about. It's basically what we want to do in science, of course, is we want to grasp some truths. We want to grasp the truth, the scientific truth, the truth that we can know about matter. And in art, we do a similar thing. We want to grasp the truth about things that lie beyond science, the things that lie in our experiences, in our inner life, in this, and we want to grasp the truths about this. And therefore, we want to grasp the truth. But if we are not truthful about this, about what we really measure, about what we really see, about what is really there, then we cannot grasp it at all. Then we will fail at doing so. So if in science everything points to a creator who created this world with design, or designed this world in a purposeful way, if everything points that way, that does not necessarily mean that we need to say, okay, you need to believe in God, end of story. That does not necessarily mean that, but it means that we need to acknowledge the fact that the science shows in this way, and not try to mingle and move around to get into this whole thing into another direction. And in the same way in art, if we have these biopics, if we have these stories, these fascinating stories that people say, hey, this we want to make a movie out of that, or we want to make a book out of that, and then, or we have this fascinating story written from Dostoevsky, which moves us deeply, and then to say, okay, we just change minor parts that we do not like, then we lose this grasp of the truth that we want to actually have, and then we cannot grasp it anymore properly. And I think this is what this delete Jesus mentality basically does. It, if you are not a believer and if you don't care about all of that, okay, but still, then you should still be against this delete Jesus mentality, because what it does is not only remove faith out of these stories, it just removes truth out of the stories. Because the truth of the matter is, whether you believe in a God or not, the transformation in the lives of, for example, Johnny Cash came because he came to faith, because he became a believer in Christ. That was his transformation. That's just the fact. Whether you believe that any truth is in there or not, the truth is that this was what led to his transformation, and therefore to ignore this completely is basically ignoring the story, is basically ignoring the truth behind the story, and therefore this is not, it's not honest, it's not truthful, and it will not grasp the truth. Therefore, these artworks cannot achieve what they try to achieve, to grasp truths that are hidden in these stories. And therefore, in the same way, science cannot grasp the truth that it tries to grasp if it ignores the points where the facts that it finds lead to. And what I argue for, what I understand that it is hard to find this balance of being objective and saying, okay, we want to show where the science, or let science lead us where it wants, basically, but at the same time also to not be too objective, to be led where science actually leads us. And I think there's also the case that you cannot, even in science, even this is shown in quantum mechanics, this is that you cannot be even objective at all, because even having some quantities that you measure, that there's already subjectiveness baked into the cake, basically, but it's another story. But speaking of quantum mechanics, I think the approach that is there taken from the Copenhagen interpretation, or this Copenhagen approach, as I call it, is the way to go. Did you basically say, yeah, we have these all these theories, so we let science lead us where it seems, and we are completely agnostic about everything else. So we say, as in the Copenhagen interpretation, you say, yeah, these particle interactions and all this stuff, there seems to be some randomness involved. We just accept it as it is. We say it is like that, we accept it, this is our interpretation, and done. And then you can have your own interpretation, you can interpret it in this way or in that way, but that's not really what we talk about here. We do science, we do it like that, and you can interpret it in all kinds of different ways, and that is fine, nice and fun, but this is not anymore science. It's more kind of philosophical science and so on, and to really make this cut. And I think this would be necessary to do this also in other ways, for example also in the theory of evolution, to just say, okay, we have the facts here, it seems to be leading to some purpose in our nature, it seems to lead to that there might be a designer behind it, but we do not really care about that. We just state it as it is, and you can make up your own conclusions from that. But to not go in one way or the other, to not try hard to in some way write God out of the equation, but of course in the other way also to not try hard to write God into the equation, but is simply stating the facts as they are, and then everyone can see them for what they are and make up his own conclusions. I think this is the best way to do it. I'm sure I know this is not as easy as it is being said, but I think this is what we need to try out to achieve, and therefore I think we need to in the theory of evolution, we need to understand that there seems to be a purposefulness in this world, and this just needs to be accepted. We just need to say, okay, this is how it is. What it means, we don't know. I know, so it means, I really believe it means that there is a creator who created each of us with a purpose. This we can see from there, in my opinion. But I think as scientists, one would need to say, okay, we just state it as it is, and beyond that, everyone can make up his own mind. So far for this episode, and so far for this podcast. So this is it. This is the last episode of the According to Sci-Faith podcast. So don't worry, there will be other episodes coming, but they will be coming from another podcast, and I will keep you in the loop about what this podcast is, and the episodes from this new podcast that will be coming then will in some parts of this podcast will also be uploaded here, and this podcast will of course remain online, so you can still listen to all the episodes and so on, but the new episodes will then also be published here, and then I will hope you will make the switch to this new podcast where there also will be some more topics. If you have listened to this episode, or you obviously have listened to this episode, so you know I was talking a little bit about artworks, about making there a comparison. I will do this, I think, in a new podcast. Also, I will also talk more only about art, mostly about literature, about books I read, what I like about those books, what impressed me about them, what I think, how you can interpret them, especially from a Christian worldview and so on. So if this is something for you, just keep in mind I'm doing this as a non-expert, so I think I can consider myself an expert in the area of science, since I studied it for more than 5 years, and I have written thesis on these topics. So I think I'm kind of an expert, maybe not the uppermost expert in these areas, but kind of an expert in these areas. But I wouldn't say I'm an expert in literature. I just read the books, and some I like, some I don't, and I talk about why or why not, and I understand many concepts of it. So maybe I'm an expert, maybe I'm not, but at least I'm not a studied one. So take what I say with a grain of salt, and it's not to say what you have to believe about it. I just want to share what I think about these, what I think about art in general, what I like about it, what I don't like. Also about my own books, of course, what I'm writing myself. I will share some of that, and it's just also for me what I like, what I think it's interesting about it, what's also I think relevant for us from this. And then you also can make up your own mind. You can also discuss with me. So I will also publish this on my Substack, and every podcast episode will also have a related Substack article. At least that's the plan for now. And then you can also discuss with me there, or to discuss with others there about what you think it is, and so on. So I'm looking forward to doing that, and I hope you will make the switch, come to this new podcast. It will be a lot of fun, I hope, and I will try to keep the schedule. So try that after this podcast episode is published, that basically the week after, maybe I will need some time. I'm not sure yet, but I hope that pretty neatly afterwards I will be able to publish episodes on a new podcast. They will be published here, so just wait for them to come, and then I hope you will make the switch and we will hear each other soon.